You should start this notes by drawing that picture.
Okay.
It's a little comment on people who want to write down every word.
John Harry Potter.
Draw the picture, right? Is it really necessary? No. How do you draw pictures?
This is not.
Okay. So, most of this we've talked about already. I'm just kind of summarizing some stuff. An electric field is similar to a gravitational field. We've discussed how they're similar. A gravitational field is defined as the amount of force exerted upon a unit of mass, and on Earth it's equal to 9.8 newtons per kilogram, right? We define that. Yeah, we know that. I'm just reviewing. As well, I'm sort of comparing them for you, showing you how they are similar. Gravitational field exists on an object with mass. That's the only requirement, that there be mass. Large masses, such as planets, have a strong gravitational field. Small objects, like the little marbles here that Zach's playing with, have a really small gravitational field. But the field does exist. Now, around any charged object, and I don't mean ones that haven't been paid for yet, thank you, there does exist an electric field. Objects with a large charge have a strong electric field. The bigger the charge, the bigger the electric field, of course. These fields are shown by a series of arrows. Notice that I didn't say vectors. Radiating inwards or outwards, and these are lines of force or field lines, and you've seen them already. Is there a picture next? No, it's on the next page. You've seen them already. Nothing too spectacular. And of course, this is what a electric field might look like. Can you tell me what the charge on the object in the middle is? How'd you know that? Oh, it says it, yeah. Because the arrows are going out. Good answer, Zach. I'll have to try to eliminate that there and see if I can get people to figure it out based on the arrows. Notice here that the arrow heads are pointing this way, but notice that the lines continue. Why do they do that? Yes, the force is always there. They go on literally forever, but they get eventually to a point where they're so far apart that, that they're negligible, right? Basically zero. Negligible. Yes, there's your second good word for the day. Note that the closer the lines are, the stronger the field, and this strength is dependent on the distance, and as Jake asked just moments before, the inverse square law does apply here. Meaning that twice the distance, 2 times the distance, means 1/4 the strength. Right? 2 times the distance means 1/4 the strength. 3 times the distance would mean 1/9 the strength. If I said 2.5 times the strength, Joey, or sorry, 2.5 times the distance. Did I say difference? 2.5 times the distance. How would you do that?
You square it by 2 and then square point.
You can go 1 over 2.5 squared, right? Yeah, 1 over 2.5 squared. I think that's 6.25 if I'm not mistaken. It's always 1/4, or always 1 over. I already did that, right? Yeah. Okay, to show the direction of the field, bring a smaller charge, a positive charge nearby, and of course it will be repelled. We've gone through all this. There's really nothing in here that's new, as I'm discovering. Right? This must be positive. Objects with a positive charge have fields that point away. Objects with a negative charge will point towards. We know all this, yeah. I'm just summarizing, right? The highlights. Objects with a negative charge have fields that point towards. We know that. Okay. This amount of attraction or repulsion can be used to indicate how strong the electric field is. The field strength is defined as the force the field exerts on a unit of charge. That's the definition. It's in the outline that I gave you yesterday. This is one of the things you need to be able to do is you need to define the electric field strength as the force the field exerts on a unit of charge. Gravity is newtons per kilogram. Electric field strength is newtons per coulomb, which you don't know a whole lot about yet. So E, standing for electric field strength, is the force. What kind of force? Electric. force per unit of charge. Okay? Where E is the electric intensity or strength and measured in newtons per coulomb. F is the force measured in our old friend newtons. And Q is this new one that we've got, charge measured in coulombs. Named after Charles Coulomb.
Why the FE?
The E just stands for the type of force, right?
Yeah.
Electric force. How big is you kind of know how big a kilogram is, right? Like what's something that weighs about a kilogram?
Marble.
A marble?
Something that's
Like how many pounds in a kilo?
like a almost 2 pound weight.
Over 2, just over 2, right? Would that be a kilo? No. The 1,000 gram mass at the back is a kilo, right? So like, I would say like
2 pounds.
a large, maybe like 1 liter, actually 1 liter of anything, juice, water specifically, is about a kilo, right? 1,000 milliliters of water weighs 1,000 grams, which is a kilogram. So think about a liter of milk. That would be about a kilo. What about a coulomb? How big is a coulomb? Anybody know? Of course not. Nobody knows anything about this. No, it's not 2 liters of milk. The intensity or strength of an electric field is the same. Now, somebody always asks me this question. I'm surprised no one's asking it.
What?
I don't even understand.
The intensity or strength of an electric field is the same for a positive charge as it is for a negative. Positive fields are not stronger than negative fields. That's an urban myth.
Yeah.
Okay, Stuart Smalley. Okay? Positive field strengths are not any stronger than negative ones, only the direction is different. Okay? Here's an example, a actual mathematical word problem example. You might want to write this one down. There's only 2. It might take up a little bit of space because, unfortunately, you're going to be dealing with numbers that are sort of scientific notation, wacky sort of numbers. So I'll pause for a second while you guys jot that down. It says, what is the electric field intensity or the strength at a point where a positive charge of 2.4 times 10 to the minus 6 coulombs experiences a 3.2 Newton force? Once I show you, you're going to go, well, that's it? Like, it sounds real complicated.
It's 3.2 over.
Okay.
Like this.
The electric field intensity is the E value. Notice here that I'm writing the formula, right? And then fill in what we know. What is the force? 3.2 newtons. What is the charge? 2.4 times 10 to the minus 6. You really should grab your calculator and try that. Make sure you, again, remember now that it's been probably a month since you've done calculator stuff. You should try that and make sure you get 1.3 times 10 to the 6 newtons per coulomb.
How do you do that? 10, 16.
You go 2.4 E or 2.4 EXP minus 6. Remember the EXP or the EE acts as the times 10. What does this answer mean? It means that for every coulomb of charge, it's going to get 1.3 times 10 to the 6, or 1.3 million newtons. That's a lot of force. That's a lot of force. What does that tell you about what a coulomb is? This is a very tiny amount, 2.4 times 10 to the minus 6 coulombs. 1 coulomb of charge is a lot of charge. It's a lot of charge. Yeah, maybe even 8 liters of milk.
No, there's no such thing.
You can't buy 8 liters of milk in one single container, but that doesn't mean it doesn't exist. You've got this fascination with milk today for some reason.
How'd you get it off of scientific?
You go, the next one is norm, I think, isn't it? No, floating, second function 4, floating. And then you have to tell how many decimal places. Second function flow. So here's example number 2. An object of charge 1.0 times 10 to the minus 6 coulombs is in an electric field of 2 times 10 to the 4 coulombs. What force is applied to the object? This time you're solving for the F. This time you're solving for the F. This time you got two scientific notation numbers to deal with.
I have that.
All right, so E equals F over Q. My electric field strength is 2 times 10 to the 4th. I'm looking for force. 1 times 10 to my 6 goes down here. This is going to be a multiply, and you should get a measly 0.02 newtons.
We change, but then that's not scientific.
It's not, you're right. What would it be if it was scientific?
2 to the minus 0.2.
2 times 10 to the minus 2. Generally, if you've only got one, like that, most people can handle. If you've got more than 2 or 3 zeros, then you should flip it into scientific. Yeah. People get confused by scientific when it's like 2 times 10 to the minus 1. People get confused by that. So what force? Why is it such a tiny little force? It's a tiny little charge. It's not that big. Electric field strength of 2 times 10 to the 4th newtons per coulomb, that's pretty big.
So this is the only true formula?
And one last tip, don't stick your finger in the socket.
What if